Hello, Year 10. This is Mr. Radmore, and this is Lesson 7 of the Triple Science Particles and Radiation 2 topic. So, we are talking about fusion today. The driving question is, why don't we use fusion as an energy resource? And your starter question is, what's the sun made of? So, the sun, as we'll talk about later, is mostly made of hydrogen. And we're going to be talking about what that hydrogen does in the sun to make light and thermal energy. So a reminder from last lesson, we looked at a nuclear reaction where a uranium nucleus absorbs a neutron, splits into smaller nuclei and more neutrons. And we successfully, on Earth, use fission reactions to make electrical energy in nuclear power plants. So we're going to look at another nuclear reaction, which in some ways is the same, in some ways is the opposite of fission. And this is fusion. So fusion is when two smaller nuclei collide together to make a larger nucleus, and energy is also formed as well. Now, to give you that in a bit more detail, this is what happens inside the sun. Two isotopes of hydrogen, deuterium and tritium. Remember, an isotope is the same number of protons, different numbers of neutrons, fused together to make a helium nucleus and a leftover neutron. So this is one example of a fusion reaction that happens inside the sun that ends up making the light and thermal energy that we need so badly on Earth. Here it is here, look. So, deuterium and tritium are isotopes of hydrogen. The nuclei collide together to form a larger nucleus, in this case the helium nucleus. Energy is also made. Now, because this is a nuclear reaction and all nuclei are positively charged, when these nuclei come together, of course, they repel each other. So in order for fusion to happen in the sun, for example, you need a very high temperature and pressure for the nuclei to come close enough that they can actually fuse in the first place. Hence, a star will only start fusing when it's hot enough at a high enough temperature and the particles have enough kinetic energy to get close enough to each other. So there it is. There's our sun. There's our local fusion factory. And as we've just mentioned, a very high temperature of the sun allows those hydrogen nuclei to get close enough together for them to fuse to make the larger nucleus of helium. So let's bring these ideas together. Which one is the porcupine, which is East London slang for lie? Pause the video. So it was in fact D, because of course all nuclei are positively charged, therefore repel each other, not negatively charged. Remember, positively charged because they have positive protons. Okay, so let's now talk about how we can go about making use of fusion on Earth. How can we tap into this way of making huge amounts of energy from this nuclear reaction? Well, we're going to need very high temperatures to start with. In actual fact, we're going to have to superheat matter until it becomes a different state to solid, liquid, and gas. We have to heat it until it becomes plasma. Now, plasma contains electrons stripped off the nuclei. So nuclei are free to wander around and the electrons are free to wander around as well. So no atoms in a plasma. It's got so hot that the electrons can no longer exist around the nucleus. Now, examples of plasma that you've might come across before: lightning is plasma. You actually get plasma inside of fluorescent lights. And other examples, the solar wind and the nuclear fireball and the aurora effects as well, are all examples of plasma. Now, for us to create fusion reactor on Earth, we need to superheat matter so it becomes a plasma, and then we need to get the nuclei to fuse together in that plasma. Now, one problem here, huge problem, is that if that plasma touches anything on the sides of a container, it will immediately cool down and transfer heat energy to the sides of a container. So we need to suspend this plasma, basically in the air. And to do that, we need magnetic fields. So physicists who want to build a fusion reactor on Earth to make electrical energy face a huge problem in having to balance a donut of plasma using a magnetic field, which typically is very hard to keep stable. Now, if we were successful in creating a fusion reactor on Earth, then of course, in exactly the same way as a nuclear power station with fission or coal, oil and gas even, we would just then use the fusion reactor to heat water, turn it into steam, spin turbine, spin a generator, make electrical energy. Okay, so fusion on Earth, a huge scientific ambition that we have. To make electrical energy from fusion. Let's bring these ideas together. Which is the porcupine? Pause the video. Okay, it was in fact A, because a plasma is a high temperature state with free nuclei and electrons roaming around, not bound to each other in the form of atoms. Okay, so why is nuclear fusion so highly desired by scientists as a possible option for us to solve our energy crisis on Earth? Let's go through some advantages. So firstly, we've got abundant fuels that we can use for a fusion reactor. Okay, we can get deuterium from water, got lots of water lying around, and tritium can be made from lithium, and we also have a large supply of lithium on the planet as well. You only need a small amount of fuel to make a huge amount of energy, which is a bit like fission. Fission, you only need a small amount of uranium to make a large amount of energy. Even smaller amounts needed for fusion, though. 10 grams of deuterium and 50 grams of tritium can produce enough energy for the lifetime of one person, a whole lifetime in an industrialized country. So it is a clean way of creating energy because we do not create any polluting gases. Most notably, carbon dioxide is not created. It's safe. We do not need to worry about chain reactions getting out of control. For example, in Chernobyl, nuclear power reactor, none of that. And we do not produce radioactive waste, which is what nuclear power stations currently do with uranium. There will be some radioactive waste created, but on a much lesser scale. So now we've got an idea of two different nuclear reactions, fission and fusion. Let's just have a go at comparing them. So let's 1 to 7 in your books. Does the statement relate to fission, fusion, both of them, or neither of them? 1 to 7. So for each of those statements, the answer is either fission, fusion, both, or neither. Pause the video. So in fact, let's go through the answers. Number 1, releases energy from nucleus. They both do. Produces radioactive waste. That's fission to a much greater scale. Fusion does produce some radioactive waste, but barely enough for it to be a problem. It's currently being used to create electricity in power stations. That's fission. It's hard to use efficiently because high temperatures are needed and a stable magnetic field. That's fusion. Has a high fuel efficiency. You can make a lot of energy from a small amount of fuel. Now that's both. Releases the most energy per reaction. Fusion releases more energy per reaction than a fission reaction. Can be used to create electricity without creating carbon dioxide. That's both. Okay, so now we've compared fission and fusion together. Let's bring all these ideas together. Pause the video. Okay, let's go through the answers. So, number one, to represent fusion in a diagram, you can simply do two smaller nuclei, becoming a larger nuclei, and energy is made. In a bit more detail, you can show the specific nuclei, the protons and the neutrons fusing together, and you get the helium and the neutron. So what is fusion? A fusion reaction is when smaller nuclei collide and combine to make larger nuclei and energy is released. Fusion is important because it's the process that allows the sun to emit light and thermal energy. And also, this is how atoms are made inside stars through fusion. So the elements of the periodic table have all been put together by the process of fusion. So why using fusion as an energy source is very challenging, because nuclei are positively charged. They will repel each other when they come close to each other. This means they need to be traveling at very high velocities. They need a lot of kinetic energy to enable them to get close enough that they can fuse together. To do this on Earth, a magnetic field is needed to suspend plasma in a donut shape. This magnetic field is very unstable. If the plasma touches the container, it rapidly cools down, transferring thermal energy, and then, of course, will dissipate, condense into gas and then a liquid. And finally, comparing fission and fusion. Fusion creates more energy per reaction than fission does. Fusion doesn't create anywhere near the amounts of dangerous nuclear waste that fission does. And deuterium can be extracted from water and tritium from lithium. So we've got fuels readily available. Okay, so pause the video and copy and complete the plenary statements. And don't forget, year 10, there's now a show my homework quiz for you to complete. I will see you for next lesson, and stay safe, year 10.